Welcome to G Fun Facts Online. Today we are diving into one of the deepest rabbit holes in the history of science. We are exploring the phenomenon known as wave-particle duality. This is not just a quirky feature of light, but a fundamental property of the universe that challenges our very perception of reality. To understand it, we have to peel back the curtain of the macroscopic world we live in and peer into the bizarre probabilistic machinery that operates beneath. Our story begins in the late 17th century, a time when the nature of light was a battleground for the greatest minds in Europe. On one side, we had the colossus of physics, Sir Isaac Newton. Fresh from taming gravity and motion, Newton turned his gaze to light in his 1704 treatise Optics. He argued passionately that light was composed of corpuscles, tiny discrete particles emitted from a source. His logic was grounded in everyday observation. Light travels in straight lines and casts sharp shadows. He reasoned that if light were a wave, it should bend around corners like sound does, a phenomenon called diffraction. Since he did not see light bending around doorframes, he concluded it must be a stream of tiny bullets. Because of Newton's immense prestige, this corpuscular theory became the dogma of the scientific world for over a century. However, there was a rebellion brewing. Opposing Newton was the Dutch physicist Christiaan Huygens. He proposed that light was not a particle, but a wave, propagating through a medium known as the luminiferous ether. Huygens could explain reflection and refraction just as well as Newton, but without the weight of authority that Newton possessed, his theory languished in obscurity. The tides finally turned in 1801 with the English polymath Thomas Young. In an experiment that would become the most famous in physics history, Young passed sunlight through two narrow slits cut into a card. If Newton were right, the light particles should have passed through the slits and created two bright strips on the screen behind them, much like spray paint passing through a stencil. But that is not what Young saw. Instead, he observed a series of alternating bright and dark bands, an interference pattern. This pattern could only be explained if light was a wave. Just as two ripples on a pond can overlap to create a larger wave or cancel each other out, the light waves from the two slits were interacting. Where crest met crest, there was light. Where crest met trough, there was darkness. The particle theory was taking a beating, but the final nail in the coffin came in 1818 during a moment of high scientific drama. The French Academy of Sciences held a competition to explain the properties of light. Civil engineer Augustin Jean Fresnel submitted a precise mathematical wave theory. One of the judges was Simeon Denis Poisson, a staunch Newtonian who believed in particles. Poisson studied Fresnel's math and found what he thought was a fatal flaw. He pointed out that if this wave theory were true, light shining on a small circular disk should diffract around the edges and interfere constructively in the exact center of the shadow, creating a bright spot where there should be total darkness. Poisson declared this result absurd and assumed he had disproven the wave theory. However, the head of the committee, Dominique Arago, decided to actually perform the experiment. He mounted a small disk, shone a light, and looked at the shadow. There, shining defiantly in the center of the darkness, was the absurd bright spot. It was named Poisson's spot, ironically immortalizing the man who said it could not exist, but the victory belonged to Fresnel. For the next 100 years, light was indisputably a wave. By the late 19th century, physics seemed complete. Maxwell's equations had united electricity, magnetism, and light into a beautiful wave theory. But two dark clouds hung on the horizon: the ultraviolet catastrophe and the photoelectric effect. The ultraviolet catastrophe was a failure of classical physics to explain how hot objects emit heat. The equations predicted that a toaster should emit infinite energy at high frequencies. In 1900, German physicist Max Planck solved this by making a desperate assumption. He treated energy not as a continuous flow, but as discrete packets, or quanta. He did not think these packets were real physical objects, but rather a mathematical trick to make the equations work. Then came 1905, the miracle year of Albert Einstein. Einstein took Planck's mathematical trick seriously. He turned his attention to the photoelectric effect, a phenomenon where shining light on a metal surface knocks electrons off it. Classical wave theory failed to explain this because it predicted that brighter light, meaning more intense waves, should knock off electrons with more energy. But experiments showed that the color or frequency of the light mattered, not the brightness. A dim blue light could eject electrons, while a blindingly bright red light did nothing. Einstein realized that light itself was quantized. It was not just a wave, it was a stream of energy packets, later named photons. Blue photons had enough energy to knock an electron loose, while red photons did not, no matter how many of them you fired. Einstein reintroduced the particle, but with a twist. These particles had frequency. Light was now a paradox. This led to a radical question posed in 1924 by a French prince and PhD student named Louis de Broglie. If light, which we thought was a wave, could act like a particle, could matter, which we thought was made of particles, act like a wave? He proposed that all matter, electrons, atoms, even baseballs, has a wavelength associated with its momentum. 3 years later, Clinton Davison and Lester Germer at Bell Labs accidentally confirmed this. They fired electrons at a nickel crystal and observed a diffraction pattern. The electrons were rippling through the crystal lattice, just like X-rays. Matter was waving. This discovery shattered the classical view of the universe. The hard, billiard ball electrons of the Victorian era were actually fuzzy, wave-like entities. By the mid-1920s, two opposing mathematical frameworks emerged to describe this new dual reality, led by two men who famously disliked each other's methods. Werner Heisenberg, a young German genius, built a theory known as matrix mechanics. He hated the idea of unobservable orbits or waves, and focused purely on what could be measured, treating physical quantities as spreadsheets of numbers. Opposing him was Erwin Schrödinger, an Austrian physicist who found Heisenberg's math repulsive. Inspired by de Broglie, he formulated the Schrödinger equation, which described how the wave function of a system evolves over time. It felt like classical wave physics, and physicists loved it because it was visualizable. Eventually, Paul Dirac and John von Neumann proved that the two theories were mathematically equivalent. They were just two languages describing the same strange reality. The philosophical battle over what this duality meant came to a head at the 5th Solvay Conference in Brussels in 1927. This was the Super Bowl of physics, attended by Einstein, Bohr, Curie, Planck, Heisenberg, and Schrödinger. The debate centered on the Copenhagen interpretation, championed by Niels Bohr. Bohr argued for complementarity, stating that an object can be a wave or a particle, but never both at the same time. The experimental setup determines which face nature reveals. Furthermore, the wave function was not a physical wave, but a probability wave that collapsed upon measurement. Einstein hated this. He famously insisted that God does not play dice, believing in an objective reality independent of observation. At the 1930 conference, Einstein proposed a thought experiment known as the photon in a box to break Bohr's uncertainty principle. Imagine a box full of photons with a shutter that opens for a tiny split second to let one photon escape. By weighing the box before and after, we could know the photon's energy and the exact time it left, violating uncertainty. Bohr spent a sleepless night pacing, but the next morning, he triumphed. He pointed out that Einstein had forgotten his own theory of general relativity. As the box becomes lighter, it rises slightly in the gravitational field. According to general relativity, time moves faster at a higher altitude. The uncertainty in the box's vertical position creates an uncertainty in time, exactly satisfying the uncertainty principle. Einstein had been defeated by his own greatest theory. For decades, the Solvay debates were the final word, but in the last few years, technology has finally caught up, allowing us to test the boundaries of duality with unprecedented precision. In a groundbreaking study published in 2025, physicists at MIT, led by Wolfgang Ketterle, revisited the double-slit experiment, but with a twist that would have made Einstein dizzy. Instead of cutting slits in a physical screen, they used ultra-cold rubidium atoms, trapped in an optical lattice as the slits. They scattered single photons off these atoms. The setup allowed them to tune the fuzziness of the atoms' positions. When the atoms were tightly confined, acting like hard particles, the photons scattered like a particle, and no interference pattern appeared. When the atoms were allowed to be fuzzy and more wave-like, the photons scattered as a wave, creating interference. Crucially, this experiment tested Einstein's recoil argument, the idea that one could detect the path of the particle by the kick it gave the slit. The MIT team found that even when they tried to minimize the disturbance, the mere acquisition of which path information destroyed the wave pattern. It was a high-fidelity confirmation of Bohr's complementarity. Nature fundamentally forbids you from seeing the wave and the particle simultaneously. Meanwhile, in 2024, researchers at Linköping University in Sweden took a different approach, linking wave-particle duality to information theory. They demonstrated that duality is mathematically equivalent to entropic uncertainty. Essentially, the missing information about the path is exactly equal to the visibility of the interference. This suggests that wave-particle duality is not just a physical quirk, but a fundamental limit on how much information the universe can hold. This is not just philosophical. Wave-particle duality is the engine of the modern world. Electron microscopy relies on electrons acting as waves to see individual atoms. Solar panels rely entirely on the particle nature of light to knock electrons loose and create current. Quantum cryptography relies on the fact that if an eavesdropper tries to measure a particle path, the wave function collapses, revealing their presence. And quantum computers use qubits, acting as waves of probability, to solve problems millions of times faster than classical computers. In conclusion, wave-particle duality teaches us a humbling lesson. Our human intuition is ill-equipped to understand the fabric of reality. We want things to be a rock or a ripple, a particle or a wave. But the universe refuses to be categorized. Light is neither a wave nor a particle. It is something else, something more complex that reveals different faces, depending on how we ask the question. As we push into the future with quantum computers and new theoretical frameworks, we are essentially learning to speak the native language of that something else. The ghost in the machine is real. It is a wave when it flies, a particle when it lands, and a mystery that keeps the universe running.